Welcome to Toilet Time. The motivation for this investigation was to gain an appreciation for something that I use every day, and until now I have not taken the time to consider what would our lives be like without our friend the porcelain throne. Who would we pray to? Imagine, in medieval times, when we would have to take a trip to an outhouse and dispose of our waste with bows and arrows. However, due to advancements in computational fluid dynamics and numerical analysis, toilets have now reached the modern age.
Welcome. I am honored to accept your waste.
The question this project is meaning to answer is, how does the geometry of the bowl change the action of the flush? And how do the boundary conditions affect the flow? This problem was set up in 2 dimensions. After the initial geometry was created, a fine curvature mesh was utilized with inflation around all of the edges. Due to the simple nature of the geometry, there exists only 70,000 nodes. This is a transient problem that was solved using the viscous model. The 2-equation realizable K epsilon model was utilized with standard wall functions for use in the near wall treatment. Only 2 Eulerian fluids were used, liquid water and air. The problem was solved using explicit iterations. The 2 solution methods used were both pressure-velocity coupling schemes. PISO was used at first because PISO can maintain a stable calculation with a larger time step and an under-relaxation factor of 1 for both momentum and pressure, and it is ideal for transient problems. I, however, got the best results when using the coupled pressure-velocity coupling and using the pseudo-transient option. The reason for this, I believe, was due to some divergence in the epsilon variable. The variables that were changed throughout the simulations were that of the 2-dimensional geometry of the bowl and the boundary conditions applied to the free surface at the top of the tank and the outlet pipe at the very bottom. Initial conditions were maintained at atmospheric pressure with gravity down for all but a few exploratory iterations and a simulation in which the negative sign was forgot on the negative 9.81 meters per second per second. As you can see from the titles on the animations, the effect of simply changing the boundary conditions and the geometry is great. Through a process of trial and error, it can be seen that sharp and dramatic changes in the outflow geometry are not conducive to the perfect flush and do not obtain the desired siphoning of waste. The best geometry is obviously the 3rd configuration out of all the trials. With the pronounced curve, an air pocket can be trapped above the first curve, and this creates the vacuum that allows the water to be discharged. In conclusion, these simulations should be continued. As you can see, perfection was not attained. However, the main takeaway was that even under the same calculation methods, initial and boundary conditions, the geometry is the most important thing to vary, as most toilets will have the same operating conditions. These animations were generated by recording every 5th iteration of the phase contours. What you have been looking at on a color scale from red to blue is the percent phase of air. 100% air is red and 0% air is blue. In the future, to further my understanding of this problem, I would of course have to take the simulation to the 3rd dimension. As is common knowledge, one of the driving forces in disposal is the vortex created when flushing. The simulation could also use a function to either shut off the water supply after a time and then restart the water supply, thereby allowing the tank and bowl to be refilled and returned to the initial state. Thank you for your time.